And let's just ignore the fact that there's any noise at all. We do know the fact here. So our dynamics are like this, right? But we do know that epsilon t is zero mean. Okay, that means the expected value of this does equal that. So maybe we can just kind of do everything like we did before, but have expected values for states instead of their true distribution over values. Maybe. That's exactly what, actually, that is exactly what we did for LQR, but it's still, you have to sort of maintain a little bit of additional knowledge there. So we can try this, right? And I'm being a little bit informal here about what this means exactly. But basically, instead of xt being just the true states, it's some notion of the expected state you think you will be in. And this, at least for one time step, holds. Remember, our big point when we introduced stochastic systems was that it did not hold for sequences of states, right? Because for sequences of states, this expectation breaks down. The nonlinear function there can corrupt that, so you don't have, in fact, the expectation of state xt plus 2 equals the expectations, you know, all these things in expectation. You can't just put expectations inside of all of them. So this is sort of an approximation to the true dynamics here, but maybe it'll work out okay. So let's try that. It's sort of the dumb thing to do, right? We just solve the problem. What it boils down to really is that we solve the problem exactly like we did before, just ignoring stochasticity because it is zero mean, so maybe it'll work out okay. So here's what happens when we do that. Here, I'm going to our 5-generator system again. And you'll remember, one of the advantages of this optimization formulation is you could also do things like put convex bounds on the constraints themselves. So in our example here, the system was linear. So actually, we sort of had the nice effects here. Though even when it is all linear, even though LQR works, once you add constraints, you still don't have optimality. So actually, the optimization formulation still is not the optimal stochastic controller. I won't prove that, but it just is something that holds. And so remember, our benefit here was that when this is linear, say for example, we still can do things like have bounds, say on the controls. So say ut is less than or equal to some upper bound on u. Maybe I'll make these not time dependent. So we have some extra constraint like all our controls have to be bounded within some amount. And in fact, in this example, remember what we did was we bounded the generation of each generator we're controlling to be plus or minus 0.5 PUs above or below its nominal power generation. So that's how we get this pattern like this, remember. And it gets kind of funny control, right? You sort of hit different boundaries and you hit other ones and you kind of move between them and settle to different levels. Now, if we do that, so what I'm solving here is this optimization problem. And what we get out of the optimization problem is both a sequence of controls to execute and the sequence of states it expects will happen when you execute those controls, according to our model. And according to our model here, without any noise in it. So here's what it thinks happens. Okay, so that's the controls that it outputs. And here is what it thinks will happen. Here's which is both what you get if you plug in those controls to this function here. It's linear in this case, so we can do that and still have it be all convex. And it's also, of course, these things are equivalent, the xt1 to t that you get out of the optimization problem itself. Okay, so it's both those things. Here's what we think will happen. But now the problem, of course, is that because this does not hold exactly, right, there's some noise in this that we don't know beforehand, but it's going to be some realization of noise when we actually execute it. What really happens is something more like this. Okay, so here is sort of, we're trying to regulate the generator angles around 0, remember? We input a sequence of control actions, execute those blindly over 10 seconds, and what happens will be something like this. And it's fairly intuitive what happened here too, right? What happened was, well, this constraint does not hold exactly. Rather, it holds plus some epsilon t, which maybe an expectation is 0, but for any given time, it's not going to be 0. I mean, probably won't be 0, right? So for any given time, there's some noise to the system, and thus we have actually this sort of bias term. I don't quite want to call it a bias term, actually. We have this extra additional term in our dynamics that makes them evolve for any given realization of what the actual noise terms are. It makes it evolve differently from how we expected. So here's what we expect again, and here's what really happens. So what do we do? This seems kind of like it puts a damper on the whole notion of doing control via optimization. As I said, the right thing to do is maintain a full distribution over all possible states you could be in throughout all time. But let's do something simpler instead. What you notice here is that at the very, and sort of this is intuitive too. So at the very beginning of this sequence here, what actually happens is not that different from what we think happens, right? So if you just look at those, the first bit here, those are pretty similar. It's sort of far down here that they really start to diverge. And that's very intuitive because in a very short time horizon, the noise might not be that big. So what we expect to happen, kind of with 0 expected noise, isn't going to be that far off from what really happens. The fact that can really knock us off is that this noise keeps building up over time, right? So we keep adding more and more noise as we execute every step in our dynamics. And so to fix that, we take kind of an obvious idea. And that is, and this is what MPC is that every time step, instead of just taking, running optimization once at time 1, and then just taking those actions, we actually at every time step re-optimize this problem using the exinit that we actually observe rather than the one that we sort of expect to happen if there's no noise in our dynamics. So here's the basic procedure. To start with, so we repeat for times 1 to our actual time horizon of the control task. First, we observe what state we're in at xt. So we observe the system state xt. We then solve the optimization problem, and I'm putting a little tilde over x and u here, and I'm also using h instead of t. We'll see in a second that actually h and t can be different. Here, h would actually be, I guess it would be t minus, big T minus little t, right? Because we're optimizing up to time t, but we're starting at up to time big T, but we're starting at time little t. And so in this case, h here would actually be our horizon, naively, would be t, big T minus little t. So we optimize kind of over all the states and controls that we have left, which is 1 to h and 1 u, 1 to h. Then we just plug in exactly our dynamics here. I'll do it for the case of a linear system. You can approximate it again for nonlinear systems, but then you have to use not a convex program anymore, so you have to use some other techniques. You have here your dynamics. So for all tau, using tau because t sort of refers to the actual time of the system, and this is sort of the hypothetical MPC time. It will be denoted tau. So you have xt plus 1 equals a, or x tau plus 1 equals a x tau plus b u tau. So linear dynamics, we'll assume here. Of course, you can have affine dynamics too. The generators are affine, so it's a little different than this even. Then the sort of initial state constraint, right? That x1 tilde equals whatever state we're actually in right then. You have also your bounds on the state and the control. And you solve this problem. And this problem will give you, every time you solve it, it will give you a sequence of states it expects which we know are not states that will actually happen if you take those actions, but it was what it expects given sort of assumed zero noise. And it gives you a sequence of controls, all the controls to execute. What we do then is we look at just the first of those controls. And this is kind of the important point. We don't look at all those controls. So here what happened is we executed all the controls, and that was kind of our problem, right? We took all these things that sort of went from now to very far in the future and executed all of them. And noise built up a lot, so what we expected to happen in our optimization problem didn't actually happen. But the first action we can take is actually pretty reasonable still, right? Because it's just based on what we do. It's just based on what we do, what our state really is right now, and then kind of guiding it towards where we want to be later on. So the last step in MPC is you execute ut. So for the real time step t, you execute the first action, u tilde 1, that you found in your optimization problem. Now, importantly, this does not mean that you only have to optimize over effectively u tilde 1 or x tilde 1. It's still very important that you solve the optimization problem with the entire horizon h, right? Because that's saying we're going to take an action. The first action is going to depend on not only where we are right now, but also where we want to be h time steps from now and everywhere in between. But then we're going to throw everything else away other than that first action we take. That's sort of the key point there. We solve it as if we were going to take all the steps, and we only take the first one. And then we let the system do whatever it wants to do, right? We sort of let it evolve how it will, and then we observe the next state, and we repeat this whole process. And what this effectively does is it closes the loop in our control as optimization framework. Because we're using what we actually see, what actually happens to the system. Xt is the true state, not our hypothetical state. We include what actually happened back into our control scheme. And as we'll see in a second, this makes it effectively work almost as well as, or in fact can work much better because it can take into account things like constraints. This works similarly to LQR and other controllers, which controllers like LQR, of course, naturally take into account what state you end up in, right? Because they are of the form, the ut equals k times xt, so they will actually adapt to whatever state you end up in. This is also effectively doing the same thing. But your function, and so in some sense, both these things, both LQR and MPC, give you the control as some function of the state. Okay, so for LQR, it's just you multiply it by a matrix. For MPC, well, ut is still some function of the current state, just a very complex function, where that function involves actually solving an optimization problem to get out that solution. Right? So in both cases, we have sort of a controller that uses the current state to determine what the next action should be. It's just that this one involves an optimization problem, this one involves a matrix multiplication. So you can also imagine which one is simpler, right? It's a lot faster to multiply by a matrix than it is to solve a brand new optimization problem. Especially if you have to control these things, hundreds of times per second. This could be pretty tough to do. Whereas this might work better. On the other hand, if you have lots of time between steps, like you're controlling over days how you're going to allocate power, you can nicely directly incorporate constraints into this one where you can't do that with this one. So that hopefully sort of demonstrates a little bit of the benefits and costs of each of these. So here's what happens with MPC. So what you'll see is that as you did with LQR, you have a policy that roughly controls the system to its desired point. Now, remember, LQR and MPC, for the stochastic case, both these things are never going to exactly get the system to its desired state, right? because that once, even if you're at its 0 state, the next time you won't be because there's some random noise you couldn't have possibly predicted. Okay, so we're throwing out the hope of ever getting the system exactly to 0. I mean, you can get it pretty close by having really big control actions, but typically there is going to be a trade-off between control and generation. Control and regulation, what I meant to say. So how close you can get to your optimal solution depends on how much you're willing to vary your control actions up and down from kind of what you expect them to be. And this was also borne out in LQR, remember. So if we go back to LQR, you could get something like this about where our generators are relative to their desired state. With that control, you get them much closer with much noisier control. And the same thing, the same exact thing bears out in MPC. By the way, the way you get these two different behaviors here is that, remember, one of the costs in LQR is this cost RU. And for this case, we have an affine system, so actually the cost is R delta U, where delta U is the difference between our kind of feed-forward control that we think will maintain the system at that state given no noise, and our feedback control. So just emphasizing the point that U is not required to be 0, or for each generator, U is not kind of being regularized towards 0. Rather, they sort of would take on this kind of average value, but it can take on other values to essentially adjust for the noise that actually occurs. So the same thing happened in LQR, and the same thing happens in MPC if we skip forward, right? So what you see here is, I think actually I just happened to pick one that was kind of in between these two things. I'm using the exact same cost here, by the way. So I'm using the same cost functions we have for LQR. The only difference with MPC is that we do have bounds. So you see these things actually limited. Even when you're sort of at the system state that you want to be in, you still may kind of wander up a little bit, and you're still going to be clipped at that upper bound in that case. So this is what the resulting trajectories and control look like for MPC. We have some sort of deviation from our kind of smooth controls you would plan from just controls optimization. You have to, because there's some noise that creates different variations than you would expect. But like MPC, you have absolute bounds on how far you ever deviate from the desired control. Not just the penalty you pay as you do with LQR, but actual hard constraints here. So that's the basic idea of MPC. It's a really sort of simple algorithm. And importantly, it's not optimal. And the second thing is that it can be pretty slow, too, right? Because, so first of all, I guess not optimal. It's not exactly the optimal control strategy you would take if you're taking full stochasticity of the system into account. So if you really represent the system as a stochastic system, you have no choice, or you really want to solve it optimally, you have no choice but to represent the actual distribution of our states at all times. That's how you have to solve it. This is an approximation which works pretty well in practice because we're essentially, just like LQR works pretty well even without knowing what's going to happen in the future. Even if the even if the assumption of LQR were perfectly satisfied, like maybe your noise wasn't exactly Gaussian, LQR can still work pretty well in practice because it has this feedback element. So if we sort of drift away from the desired state, we kind of push ourselves back there a little bit, sort of like a PID control does, right? A PID control didn't have any notion of optimality, yet it kind of worked okay. MPC is a similar thing, where it's not optimal really anymore, but if you get far away, it'll sort of plan a trajectory to get you back to where you want to be. You'll take the first bit of that, and you'll see what happens next, and you'll keep doing this, and that will tend to push you back toward where you want to be. So this feedback element can work very well in practice while, as I said, obeying those constraints that we have on our control. Now, a big problem here, admittedly, is this is not a simple task. To compute this effective function for MPC requires we solve a big optimization problem every single time. So for example, in this last plot here, I use an integration time step of 0.01. So there's 100 intervals per second of what happens here. That means that an optimal horizon of 10 seconds, right? And even using kind of I saw this before just as optimization, or in the discrete time case using YALMIP, and it took like a couple seconds. I actually even went further and optimized it with a solver called Cplex, which is sort of a very fast, for off-the-shelf software. It's a very fast solver. You're not going to get that much faster for QPs like this, quadratic programs like this. So even after I optimized as much as I could, for a time step of 0.05 seconds, or 0.01 seconds, optimizing for a horizon of 10 seconds, that's 100,000. Sorry, no, 1,000 states, but then you have a lot of states per thing. So you have 5,000, so it's like 2,700 states, right? That's a lot. And that many variables in our optimization problem. It still takes about 0.25 seconds to compute the solution. But unfortunately, my actual integration time step that I was thinking about was 0.01 seconds, right? So I'm not even as fast as real time. So if I wanted to actually control a system like this, I couldn't even do it, because by the time I had solved the problem, the system would have moved further forward than I had actually planned for. So this seems like a problem, right? Even, and I should say, this is 5 generators. That's tiny, right? There's many more generators in the actual grid. How do you actually go about applying this in practice? Well, first of all, I should say that as I said before, the first thing you might want to do is just forego using MPC for a problem where the time step is this small. So for something like scheduling generation over days, where you're looking at really more the economic dispatch problem, minimizing cost, sort of the optimal power flow problem with time constraints. When you look at that, you're talking about maybe taking 1 action per hour. This could work great. Maybe you don't care that it takes an hour between, it takes 0.25 seconds between things. If you're waiting an hour between what you actually do, that's probably fine. So it could be that for some problems, and I'll really admit this, that for some problems MPC really isn't that well suited. The number of tasks where it can be applied, though, is increasing a lot, just because computational power is speeding up. A decade ago, MPC was sort of unthinkable for any kind of real-time control task. Now it's used there all the time. Maybe 2 decades ago, it was unthinkable for that. Now it's used there all the time. Okay, so there is some sort of natural progression of computing which will make this more applicable. But even then, if I have a system with 100 generators, for example, instead, I don't think I'm going to get this down to the right size that quickly. I just don't think it's going to really happen. So what do we do? So what I'll finish up with for today is some methods for speeding up MPC and making it more practical for real situations. So the first one is that, and I'll write down kind of the basic MPC algorithm here to have it in mind. So remember, our first thing was we observe xt, and we solve the optimization problem, minimize over x tilde, 1 to t, or 1 to h rather, u tilde, 1 to h, sum tau equals 1 to h, cos x tau, u tau, subject to, I'll write the sort of general case here, but for a linear system, this would be make it all convex. Or an affine system would still be convex. Oops, equals. And then x tilde 1 equals xt, where xt is the actual state here. And then finally, we take action u tilde 1. Okay, so here's the first point. There really are two effective horizons we care about, time periods we care about when we have a control task like this. Right, remember, we're doing this whole thing for 1 to big T, for 1 to big T. Right, and big T is the time horizon we actually care about in our control task. And that can be a really long time, right? Because maybe we care about regulating the system for days. We want the system to be, stay around. We probably actually want it to stay around the right part forever, in theory, right? So in theory, actually, big T is infinite, because we want to continue this process forever. So really, we care about kind of the sum of infinite number of costs. And LQR actually worked for the infinite time horizon thing, so that actually was fine. In MPC, we can't do that because we can't actually store an infinite number of data points. But the big point here is, and what I sort of said was that, well, we could pick h to be equal to t minus little t, meaning that wherever we are right now, we schedule what to do for the rest of time till the end. Okay, but this, while it's sort of the right thing to do in some sense, often isn't really necessary. And here's the intuition. If you're trying to regulate generators around some desired point, some desired angles for all of them, I probably don't really care where they're going to be tomorrow. And if I'm able to reach that desired point in maybe 10 seconds or so, I probably don't really care what they're going to look like tomorrow. Right? 24 hours from now, if it takes me about 10 seconds to get them to where I want them to be. So there's no need to take our horizon, for our planning horizon here in MPC, to be the same, to be this actual equation here. That says that we sort of care about the rest of time up until whenever. There's no real need for that. MPC can work very well if you take h to be some much shorter and even fixed time horizon. If it's too short, you have this problem where you're not looking far enough ahead, certainly. I mean, that was sort of the point of control, is that we don't want to just optimize, say, if you take h equals 2 or 1. You're not going to take any actions that sort of steer you towards where you want to be in the long term. You'll just take kind of greedy actions right now. But if h is long enough, such that and long enough is very kind of problem specific here, certainly. It's very dependent on the particular problem. If h is long enough such that it kind of looks far forward enough, right, then this can still work pretty well, even if h is much smaller than the big T minus little t. And of course, by doing this, we can greatly reduce the amount of computation we do, right? Because we can go from needing a really, really big optimization problem here to needing a much smaller one to solve only some solve these problems only for some finite time into the future. Okay, so here's what it looks like. So here is our control law. If we take h to be equal to 10 seconds, and I'm actually having it be 10 seconds, but then I'm also clipping it to be the maximum, so I'm, once I'm at the end, you don't need to take more than 10 seconds after you reach time t. But you still can, by the way. You could optimize, past your time horizon t if you want to. There's nothing stopping you from doing that either. So here's what it looks like if I take my time horizon to be 10 seconds. That's as long as my what I'm plotting here, and just for the sake of this argument, we'll say it's as long as we care about. I don't know why you care about only for 10 seconds, but say we do here. If I do the exact same thing with my horizon being 2 seconds, I get this. Now, even in 2 seconds, notice we're not actually reaching our optimum in 2 seconds. So it's not like this is enough to actually get there, even here. But it still works really, really well. I think you'd have to squint. I can't see the difference between those two graphs, for example. I think if there is some, it probably just has to do with random noise more than the actual control law they apply. I actually might even fix the random noise sequence, though. So these look actually pretty much identical to me. I don't see any differences. Maybe there's like a slight, I'm looking for like a little pattern, see like a little different. Maybe there's a slight difference there, but they're, for all intents and purposes, identical. Okay? And that is with only optimizing 2 seconds ahead instead of all 10. So we've shaved off, 80% of our computation, and it looks exactly the same. Of course, how short you can go is going to be very problem dependent. So here's if I start going shorter, here's what happens. So this is h of 0.05. That still maybe is okay. It sort of looks all right. That one doesn't look too different. Actually, it's not really getting to 0. So I'm kind of staying, maybe I'm taking actions that are too small. I'm not really driving it. I'm not looking far enough ahead to really drive to 0. But maybe it still is kind of okay. But you see sort of real problems develop when you get too short. So this is h of 0.1. And what happens here is that 0.1 seconds for this problem is just far too short a time period, at least also given the cost that we have, is far too short a time period to really be able to do much to the system in that amount of time. You can't get it very far unless you're willing to take huge actions, which we don't have available here in this MVC framework. So we have a limit on how big our actions can be, and so it's going to take us a long time to get to the end. Or rather, it will take us more than 0.1 seconds to get anywhere where we can actually control the system in any meaningful way. So what happens is, it isn't horrible, actually, sort of almost surprisingly, right? It's actually not the worst thing you could do here, but it's not really going to control the system in the proper way. So of course, that's also 1/100th of the computation. And as you might expect, it turns out that sort of the right place to be is typically some balance in between those two. So you want some amount of, you want to look far enough ahead that what you do will sort of be thinking about the long-term consequences of your actions, but there is a point in which looking further ahead will not actually change what you do. You will do the exact same thing whether you look forward 10 seconds or a day. So don't look forward a day. Okay, so that's one. Were there any questions about this one? Okay, the second thing is sort of similar, but it's a slightly different point. In MPC, so the first thing we could do was shorter time horizon h. The second thing we can do is to update this whole thing less frequently. So a big problem with MPC, what reason why it's so slow, is that we are solving this optimization problem very, very frequently, then taking only the first action that we get out here. That's very time consuming, of course, because, well, you have to solve an optimization problem to get there. And you're doing all that work for only one action, only one control. And if, by the way, if your time has passed in that time point, you've already missed your chance in some sense, maybe. So the second thing we can do is the idea here, well, backing up for a second, the idea of MPC in general was that we wanted to take into account how what was really happening was different from what we expected to happen due to this noise, right? But in the very short term, so my time step here is 0.01 seconds. In the course of 0.1 seconds, say, the amount of noise that will actually build up in the system is pretty small. So we're not actually going to go that far off from where we thought we would be, probably. So basically, our hallucinated x tilde, for the first maybe k of these, say, where k is like 10 or 20 or so, is not going to be that different from what really evolves. So rather than just taking the first action here and doing this every single time, you can do this only every, say, k time steps. So maybe sort of, I'll write it like this, if mod t k equals 0, so if k is some number, say 20, and if k divides t evenly, then you do this. And rather than taking every single, only the first action, you actually take all the actions, your hallucinated or your planned actions from now to step k. With the intuition being that in k time steps, your hallucinated state here won't differ that much from the true state. It will somewhat, certainly, but not that much, maybe. And again, the idea here is that over a short time horizon, the effects of stochasticity are not that bad. They're somewhat small. So you're not going to build up huge error. Okay, so here is a plot of these things. And again, the top plot is updating every 0.01 seconds. That's every single time step we take in the integration time step. It also kind of speaks to the fact that our integration time step was somewhat arbitrary here, right? I mean, why would we choose 0.01? Well, that's just what I chose as my delta t. I could choose anything. We probably don't need to pick, our optimization problem entirely dependent. Don't make it entirely dependent on whatever I pick for my integration time step. So what I'm showing here on the second plot is if we do the updating of MPC only every 10 time steps. So in other words, we update the MPC solution every 0.1 seconds instead of every 0.01 seconds. And again, as with the first plot with the different horizons, there's hard to tell the difference between these two, right? Effectively, taking 10 steps, so taking actions 1 to 10 looks identical to taking actions 1 to t. Despite the fact that that's you have a whole lot less. You're feeding back your state a whole lot less then. As with the shorter time horizon, though, you can kind of start taking this too far. So if we start updating every 0.05 seconds, well, that actually looks pretty good. Do every 2 seconds, well, now you start getting back to the same situation we had with this optimizationist control in the first place, right? Where our state starts to diverge too much from what we expected, and so you get this very weird behavior where things just kind of float around where they want to be. They don't actually ever reach it. Or you don't feed back often enough to actually regulate your state where you want it to be. So the second thing was essentially less frequent. Now, by combining both those two things, and what we saw, right, was that, okay, maybe we can take updates every 0.5 seconds. That's a 50-fold decrease in computation. By using a horizon of 0.2, we can get 20%, I guess a 5-fold decrease in computation. So by doing all this stuff, as you might imagine, we actually can get a system where we can solve it in real time. So I think for on my desktop here, I can take a horizon of 2 seconds, update every 0.1 seconds, and then to solve it in my optimization solver takes now about 0.08 seconds. I've reduced the amount, so I've reduced it 10-fold with the different updating. I've reduced it 5-fold with the horizon. That makes the computation a lot less than it was originally. And because of that, I can get it down to taking 0.08 seconds to solve the optimization problem, this one right here. And we need to sort of resolve it every 0.1 seconds. This is now at least able to keep up with real time. Basically, by the time I solved it, and it's sort of weird because I've moved on a little bit, right? So I'm still taking these actions, but I've moved on a little bit from now. So maybe I don't quite take like the first k, I take the k8 to k plus 8 or something like that. But still, I can kind of keep up with the system in real time. As long as I can solve things faster, then it sort of gives me new states. So that's good. We now have an MPC system that, even for a pretty high frequency control task like this, still looks reasonable. Of course, this is still relatively simple, this task. have to say, right? It's still 5 generators we're talking about, controlling them to regulate their angle at around a given point. That's not a very hard control task. And so even 0.08 seconds seems like a lot of time to solve that one. It's a pretty simple task. So again, there are pluses and minuses here. MPC, as I was saying before, it finds most of applications in times where there are larger time steps between different actions. So, where you take a new action every hour, every 15 minutes. Then it makes perfect sense, right? Because then you have a lot of time to sort of spend doing computation to find the best thing you can do in that next 15 minutes or hour. If you have systems that sort of change really, really fast, it might be less applicable. But having said that, there are a lot of cases where this works a lot better than LQR. And so if you can develop a solver that will actually solve this problem fast enough to keep up with real time, maybe you really do want to go with that instead of going with your more traditional control law like PID control or LQR. So the third, or rather the bonus question on the homework, that covers essentially an optimization formulation of planning for a smart grid domain where you have some storage, some wind power, some generation you can control, stuff like this. And you can apply exactly that kind of stuff in an MPC framework to figure out what to do not just now, but all times as you go forward in the future. And so that's where this kind of stuff can play a big role, because then that's what we're talking about planning every hour or so. And maybe that's where this stuff really makes a lot of sense to do. At 0.01 seconds, maybe it does. I know people actually talk about doing even faster than this. So because so for small enough problems like this, if you reduce your horizon enough, maybe you have a pretty simple control task where you don't have to have that long a horizon. You can only look, taking actions every so often. You can make this problem pretty small in some cases. In those cases, you can actually develop kind of specialized code just to solve that problem, which can be very fast, on the order of milliseconds or microseconds even. In which case, it actually can make sense to do this for even very sort of high frequency tasks where you have to change a lot. So actually, one of the most interesting current directions, I think, in control is exactly this: finding domains where you can do MPC at extremely high frequencies to get this kind of control, optimization-based control, in a framework where typically that wouldn't have been imagined 10 years ago. That MPC was for controlling big factories, maybe, not for controlling like a little robot or something like that, or not for controlling generators in a grid. It was for doing dispatch, but not for real-time control. But it's becoming more and more applicable to real-time control every day, every year. All right. I guess so. I forgot I had a slide here. So I guess this was what I was getting to before. The third, obviously, way you can speed it up is just to optimize faster, right? I use CPlex. That is faster than YALMIP. YALMIP wouldn't have solved this because it would spend a little bit of time parsing it and everything like that. And so that actually would be a little slower. If you can put the problem into standard form and directly use a specialized solver or an off-the-shelf solver like CPlex, that can be a lot faster. As I said before, even faster than that is if you develop custom code to solve just this one problem. You can do that too. So you're essentially using the same techniques that these general purpose quadratic programming solvers and linear programming solvers use. But you can do it with a lot of sort of tricks that can make it faster. For example, something that happens in MPC a lot is that, or in optimization, even convex optimization, which has a global solution, a big task in optimization is to figure out a starting point you can start from. So you get next to where you basically start from in order to get subsequent solutions. Typically, optimization procedures are iterative, so they start at one point and then slowly have to get better. So if you give it a good initial starting point, this can work much better than if you get a bad initial starting point. Now, a common thing to do for your starting point is to take the solution of the previous optimization problem and use that to initialize your next solution, right? Because that was sort of what you would have done had you just executed stuff blindly. Or say, you take x tilde or u tilde 2 to h, and then maybe repeat the last action, something like that. So u tilde 2 to the h, and then h, u, h again, as your initial guess for what you want to do at time 2. Right? Because that's sort of what you thought you were going to do. It's probably going to be something similar to you. It'll be a little different because this will not be quite what you hypothesized your state would be. But if this is kind of small, that's a pretty good starting point for how you want to initialize these things. That's one simple kind of optimization procedure you can take into account. You can also do things, as I said, like create custom code just to solve this one problem here. And there's some really cool work on essentially it's code generation. So you give it just a description of the problem, and it will this program will actually generate another program which is meant to solve just this one instance of an optimization problem. And that can be applied. That can work really, really fast, and it can be applied really nicely to these kind of domains where, say, maybe you want to solve this thing on an embedded processor. So you want to develop some small piece of code that's sort of self-contained that will solve just this one problem. There's some very interesting work on doing exactly that. OK, so that is basically all I have for control. I have 2 slides at the very end of this, and then we'll be done for the day. But one thing I wanted to mention through all of this is that the dynamics that so sort of an overriding assumption in a lot of this unit on control in general was that we had dynamics, of the form xt equals f, xt plus 1 equals f of xt ut, or even for a linear case, xt plus 1 equals a xt plus b ut. And a lot of these things, basically everything except PID control, assumed that we knew what these, say, a and b were. So for LQR, you have to plug a and b into that LQR command in MATLAB in order to get a controller out. For MPC, you have to put these 2 matrices into the optimization problem itself for it to solve itself. And they all require that we actually know what they are. Right? But in practice, there are a lot of cases. Say if you want to heat a room, we talked about how that sort of is based upon physical laws. That's true. But I don't know if that's always the best way to, physical laws can be complex even for a single room. I mean, this room has, I don't know what the thermal properties are between the window and the inside here. I don't know exactly what the thermal gradient is, or not the gradient, what exactly the conductivity essentially is between the outside and the inside here. So it could be pretty complex to kind of, open a book of physics, figure out the exact properties of that glass, all these kind of things to get a precise model of this room. Just again, from first principles. So this is sort of where, and that is required in order to apply these, some description of the room is required in order to apply these methods. So this is, again, where things like machine learning can come in. And the integration of machine learning and control is, I think, one of the sort of the most exciting areas of research right now. What happens when you have systems that are always learning new models of the world and trying to control them simultaneously? So in the case of this, I'll just talk about linear systems right now. Suppose that we believe our system to be linear, or approximately linear, but we don't know what A and B are. Well, what I've said sort of is that this is a machine learning problem, but I just want to formalize what that is exactly. And what I mean by that is we can observe a bunch of times where we see the next state and the previous state and previous control. So we have a bunch of pairs like this. And in machine learning context, this essentially is the outputs, and these here are the inputs. Apologies for using x twice here and y for something that's different. I'm trying to, again, merge between the machine learning and the control notation. Now, the one difference here is that from what we saw typically is that y itself is a vector in Rn. It's not a single quantity anymore, it's a vector. So we need predictors a little bit different than what we saw before. But actually what we can do is just take each element of y individually and frame this as a machine learning problem. So what we might have is we might have, y, or rather y equal to xt plus 1. I shouldn't say that this is for a lot of t, right? This is a t for 1 to some big T. And we have the next one, the next state, current state, and current action for all these t's. So y could essentially be the, for one task, y could be the ith element of our state, the next state. X could be all of our current state and current control. Maybe I'll write it like this, actually. Xt, ut. And now this is just a linear prediction problem. If we want to find a linear A and B to do this, this is exactly a linear prediction problem here. This is exactly the least squares problem, where our phi actually, in this case, just is this thing. It is just ut, and it is just x, which is ut and or xt and ut, and our output y is xt plus 1, the ith element of that. So a little more details here. Remember, what we can do is we can compute or we can observe some sequence of controls and states. We can get that any way we want. Maybe we start with a PID controller or something like that, right? That sort of does OK, but generates enough data such that we can learn a model of the system. So we start with some data like this. We find A and B that minimize this thing here, which this thing is now a sum of loss functions. I'm actually writing right now sort of the machine learning problem for minimizing all these tasks simultaneously, effectively. So we're actually looking at all the y's at the same time. That's actually equivalent to looking at all of them individually and just concatenating the answer together. We can also use other loss functions. Instead of least squares loss there, we can actually use L1 loss, whatever we want, to get different estimates of these A and B matrices. And this, at least if we use the L2 loss, this is a linear least squares problem. We know exactly how to solve it. It just involves basically, you form a big matrix of all these guys. You do phi transpose phi inverse, phi transpose y, and that will give you the solution. That will give you A and B. Now, one big point here. If the system really is linear, this will work very well. If the system is really linear, then, and maybe with some noise, for example, then all your data will sort of come from the same linear model plus some noise. And they can kind of be all over the place, but you still can kind of do OK. Or sorry, regardless, so actually, let me sort of draw this picture here. A few minutes we have left. So if your data is really linear, I'm going to draw it like this. So our output, which is, again, think of xt plus 1 here, and x, say it lies approximately on a line. If it really is linear, then it doesn't really matter where you get data from. So I'm going to have a few points over here and a lot of points over here. And least squares will sort of fit, no matter what you do, it'll sort of fit this line pretty well. So it'll do the line. If you have a situation like this, though, where your system is not linear, then a quick point here is that it really doesn't matter now where you collect your data from and how you collect this data. Because if you have a lot of points over here, then what least squares will do is actually fit a model kind of like this. Because this fits this data really well. It makes mistakes here, but you only pay for it 3 times. Whereas you get a lot of benefit over there. But then if you end up taking control actions that sort of put you over here, this is maybe the best place to be in your system, you just ended up over here in your training set, that's really can be nasty. Because now you've basically ended up in some place where your model is completely wrong. So this is actually one of the most kind of subtle but hardest points about this iterated learning and controlling framework, is that where you get your states from matters, and that can greatly affect both what you do next time, so sort of where your controller sends you in state space, and it can easily send you to some place where your model is actually very bad. So it's easy to kind of get caught in some bad behavior here where you do something that looks good, but that sends you to a place where your model is actually very bad. OK, so this is actually the end of our official units here in this course, the 3 units. So we're finishing up control now. I'll ask if there are any questions, but people have, I know people are probably antsy to go. The next few lectures are kind of going to be becoming special topics. So we'll have kind of special things. There's also, we'll have sessions for asking questions about the homework and stuff like that too, if people are curious. But mainly we're going to be talking about kind of topics that come from here and there. We have 4 lectures left, I believe. So we'll sort of have 1, and then we have a final lecture on the last day of class too that sort of wraps up a lot of this and talks about some future directions. So, OK, are there any questions quickly in the negative 1 minute we have left? OK, see everyone next time. OK, so today we're going to start really the last set of lectures. So as I said last time, we really finished the actual main units of the course with the lecture last time. So that's all you'll need to do all the homework, I guess is the, the short way of saying that. But of course, we have 4 lectures left, and in that time, I want to give you a little bit of introduction to some more advanced topics. Today is actually going to be a pretty broad overview of some of these topics. We're going to cover these 4 things in quite little detail, I should say. I mean, we'll present the problems and sort of get the basic setup going here, but we're not going to sort of delve deep into the math behind actually how people approach these things. I'm mainly sort of pointing you to the problems and then the future, the papers and other work in the area that actually addresses some of these problems. So that's going to be kind of lectures today. Next time, I will focus on one particular area that I work in, which is this problem of disaggregation of energy, right? So if you have I mentioned this a little bit when we talked about the classification in machine learning, but if you have a whole building and you want to figure out what's going on, how the different sources are combining to add up to that total aggregate power, how can you actually break down power from just the whole home signal or whole building signal? And then on next Tuesday, I will probably actually go over the extra credit homework problem in problem set 4. So it's due on Tuesday. I really encourage you to look at that and try to make some progress in it. It's sort of taking a lot of what we put in class, what we've been doing in class, putting it together. But at the same time, it is sort of an advanced project. And last year was actually, it was basically the entirety of the problem set, and it caused a lot of problems because I think there are some stretches you have to do. It is a little bit more of a research topic rather than sort of just doing what we presented. So I didn't want to make it mandatory this time. But I do encourage you to look at that, and we'll count for extra credit if you do want to do it, so you can get a few more points. And I'm going to go over the next, I guess, a week from this Tuesday. And then the last class will be finishing up anything else that we don't get to in that time. But maybe we'll go home early that day. So first of all, I guess since we do, and I really do hope everyone comes to these last 4 lectures. I know they're not going to be referenced in the homework because the homeworks are all out. But this is, in some sense, kind of the most exciting topics in a lot of degrees, right? Because these are the things that are currently ongoing. They're kind of taking a lot of what we've done so far and putting them into what is actually going on in the current state-of-the-art research that you see published on journals like IEEE Transactions on the Smart Grid. So they're meant to be kind of fun lectures. It's not going to be tested, but they should hopefully mean they're meant to kind of stimulate some ideas and some conversation. But because of that, I also wanted to pause for a second and ask about the homework. Are there any questions on the homework? Mainly people were just emailing me, which is fine. If you have any outstanding questions that I did not address in my responses to you, then let me know. But are there any, or if you have a question that you haven't asked me yet, are there any questions about the homework in general? Yeah?
When we are doing some of the control problems,
yes.
For the reference generator, is that like usually or always the slash generator? Or is it kind of arbitrary? Like doesn't really have
The reference generator, I'm a little unsure what you mean by the reference generator.
like the angular velocity.
Oh, so omega reference is a fixed number. It actually is not based on any generator. Omega ref is always 60 hertz. So it's always, you know, the thing is that you don't actually have to worry about what it is for our sake. I mean, you can, but the thing is that it's all, basically your omega, all that matters is omega minus omega ref. So basically what matters is your deviation from the true thing. So if you set up your set of equations such that your state variable is omega minus omega ref, then you don't have to worry about it at all. I think that's how I laid it out in the homework assignment. So actually, does that make sense to everyone? So the idea being that if your state variables are theta and then omega minus omega ref, omega ref here is 60 hertz. So it's 60 times 2 pi is the actual value of it. But if this is your state variable, then your state already encodes this. So your equations of motion really are that theta dot, which is x1 dot, equals theta dot, that is just going to be x2, right? Because x2 actually is omega minus omega ref. And similarly, the equations of motion that we gave have an equation for x2 dot, which equals really omega minus omega ref dot. But because the reference angular velocity is not changing, this just equals omega dot, which equals, right, because this one is not changing with time, and so which equals this, 1 over 2h p mechanical minus p. I guess we call this just ut here, so this is just the ut minus p elec. Okay, so that's how I set it up in the homework, because I actually didn't want you to have to worry about what that number actually is. Intuitive, and the reason for this is that what we're really tracking here in theta is not the actual Adobe, don't want to install. This is like the most common interruption, I think, in of any program, right? They like somehow manage to. There we go. So I didn't want you to have to worry about sort of what omega ref was, but the important part is that theta. If you think about the angle of a generator, well, this generator itself is spinning many times a second, right? But we don't care about the absolute angle of that. What we care about is where is this angle relative to everyone else's angle. And so because of that, the way that theta changes here, really theta is a deviation from where it should be in some globally synchronized rotation. But again, what actually that means is not, that's sort of our slack generator thing, where the actual reference is sort of unimportant. But what is important here is that because of this equation, I mean normally the derivative of an angle is just angular momentum. So normally you just have theta dot equals omega. But here, because we're tracking the difference between theta and its desired angle in some sense, these are our equations of motion here. But I think the take-home message is that you don't have to worry about what omega ref is. You just have these equations of motion, and then everything is sort of being taken care of. Yeah?
Do you have any insight into choosing the Q and R matrices for the cost of QR?
Yeah, so Q and R, the choice of Q and R is it's just sort of, this is sort of the magic. This is sort of like the art of controller design, right? So in some sense, I talked about how great LQR was because it's optimal control instead of PID control, which is just gain tuning. But LQR involves plenty of tuning itself. It's just cost tuning. So you will tune the costs. Now, the difference is that it typically is a little bit more intuitive to tune costs than it is to tune gains. Gains are just, they're kind of arbitrary what they actually are, right? It's just sort of, you have numbers that all interact in weird ways, whereas costs, I mean, there is certainly interaction between them, but essentially, if your theta is too far from theta desired, then you turn up the cost on those terms. Typically, I don't think I've ever used a cost matrix that is not diagonal. You could use a full matrix for the cost, but I always just use a diagonal matrix. That, actually, so let me clarify what I mean by that. Your cost is something like Q times X, right? And that actually works because, again, our desired angles are 0 in this case, and our desired angular rather the desired deviation for angular velocity is also 0, right? You want to keep those both at 0. So this is our cost, say on the states, and we also have one on the control inputs. And the nice thing about this is that I typically will choose Q to be diagonal. So Q equals some diagonal matrix here. And I usually, I'll just start with the identity, say. And this, this block here is going to be for the x1 variables, because really we have all our x1s, sorry, this block here is going to be for all of our theta variables, and then the next block is going to be for all our omega minus omega ref variables. So this is sort of the theta block here, and this is the omega minus omega ref block here. And so you just choose it to be diagonal, and essentially if you're not tracking your theta well enough, then you say, well, this isn't high enough, so I'm just going to bump this up to, say, 2 here. I'll make these all 2. I think it's all at 1. Or it's obviously bigger than that, but you have to do the proper sizes. And this, with diagonal matrix here, this qx squared is just going to be equal to sum over all I of qii times xi squared. So all it really is I'm just weighting each of these functions individually and calling that my cost. Now, in this formulation, you can choose an arbitrary q. You could have some q that kind of couples these things and say, my cost is some function of both these things at the same time in a quadratic form. But that's much less intuitive, right? That already is getting complex to me. I'm not quite sure to think about that. Unless, by the way, you want to include something like my cost is something like x1 minus x2 squared. Then you can actually encode that as a q matrix. So you can do that. But for when your cost is something just like I just want all these things to be close to 0, then typically you just pick q to be diagonal. And same with r. R is just a diagonal matrix usually that weights your different how much you care about the different controls. I should say that is the fact that they're diagonal. You should not use that in your mathematical derivation, because in theory they are allowed to be non-diagonal. It's just that we typically in practice take it to be diagonal. But you should prove it in the general case for your least squares derivation. But yes, essentially it comes down to if it looks wrong, you tweak the numbers a little bit, and then hopefully it looks better. If your controls are just too big, they're just sort of flying around too much, you have too big of magnitude, then you just increase the cost on R. Now, you can't play this game forever, right? I mean, there is a limit to the performance of the system. It's not, you can't just get perfect performance and have 0 control. You have to trade them off. But finding that trade-off is typically a lot easier than just guessing what the numbers are in the controller itself. Anything else? So I also sent out comments to everyone about the project milestones. So you should have gotten those. If you haven't, then come see me. But also welcome to, email me back or come to office hours to chat about those. We are having office hours as normal next Monday, so just come by. All right, so let's talk about some future directions in smart grid research. As I said, this lecture in particular is going to be pretty high level. The next one I'll dive into a little bit more detail, and then on the next one after that, I'll go into a little even more detail on the challenge homework problem. Essentially because that does capture a lot of what we've sort of been covering through the whole course, so I think it's actually useful to actually go through it and see the solution. And sort of go through rather than just have the write-up, because the write-ups, they can be kind of hard to parse. I write kind of dense code to keep everything short. I hope to make it readable, but sometimes it isn't always that readable, especially for that problem. That problem is very kind of long. Okay, so as I was talking about, and as you can probably imagine, and this is just covering a few of them, there are a huge number of directions for future research in the smart grid. So this is not an exhaustive list by any means, but here are some things that are actively being worked on. And if you check out a journal, I think that this is actually a link. So at least if not this one, then all the others are links. There's mine. Here I am. Oh, it's hidden. Oh, well. That's right. I had the cursor when it's over that. Oh, well. If you download the slides, you can click on most of the papers that I have in this set of slides. You can click on the link to, and you'll go to a web page that at least on campus, because they have all the right library privileges, at least on campus here, you can go and actually download the PDF then for the corresponding paper. So these slides in particular, download them and check out the links if you're curious about any of the results or sort of techniques presented here. These are some of the things, and we'll cover 4 of these. This one here, smart homes and energy disaggregation, that one I'm going to cover in more detail on Tuesday, so I won't cover it that much today. But the other 4, I'll just mention briefly what they are. Renewable integration, grid security and resilience, demand response, and then microgrids. I'll cover each of those in some detail, but mainly point you to papers that are related to that. If you do want to look at sort of other research going on in this area, this journal, IEEE Transactions on Smart Grid, kind of is one of the new de facto journals for a lot of this research. As you can imagine, it's called Smart Grid, so there's a lot of research on the smart grid in it. I will say that it's not that the quality of papers in a lot of the smart grid journals are not at the level of some other more mature fields, to put it sort of politically nicely. That's just sort of a natural effect of, a new area they're trying to encourage work in it. What I mean by that is do not go to this journal as a source of all sort of canonical knowledge for the smart grid. It's good, there's some very good papers there, but they're not all fantastic. I think some of them are just kind of, they're okay. They're good pieces of work that are maybe kind of narrow. It's not like Science or Nature where you just see only nothing but great articles. Check it out, but don't treat it as sort of the, the end-all be-all of smart grids research. Has anyone actually ever read any articles in IEEE Transactions? A little bit, yeah. So they sort of vary, right? They kind of, okay, yeah. It's a fair assessment, I guess. It's getting a lot better, certainly. And it is the place where you submit stuff for smart grid research. Okay, so let me talk about each of these in a little bit of detail now. And I've touched on some of these topics a little bit in class so far, but this really is more highlighting the problems that we have going forward rather than solutions. I mean, the class has been largely kind of solution-oriented. We talk about algorithms for machine learning and for control and for power systems, but we haven't really talked about maybe some of the bigger problems and bigger open questions that still remain. So the first one I'll talk about is this problem of renewable integration. So most of you have heard that term at least. Essentially, states, and for many reasons, but actually for sort of political reasons, it usually happens at the state level, just because it's easier to pass stuff at the state level than nationally. A lot of states have instituted what are called renewable portfolio standards, which essentially require, usually, but by a certain date, some fraction of their energy has to come from renewable sources. So that's to come from wind, solar. Some of them count hydro, some of them don't. Some of them also count like energy efficiency into that thing, so they kind of try to get back to other routes. But they have pretty ambitious targets here. So for example, a famous one is California, who, and I believe this is still on target, or they're still aiming for this certainly, that by 2020 they want to have 1/3 of all their energy come from renewable sources. And that's going to require a lot more wind and solar because essentially in terms of the hydro, they're more or less where they're going to be. They're not going to build a whole ton of new dams in that time. And the reason why this is so hard is that unlike, and we did sort of mention this before, but just again to drive the point home, unlike traditional generators, where in power flow and optimal power flow, you can decide how much they generate, right? That's sort of a result from the optimization problem of optimal power flow. And when the ISOs, these grid operators schedule power, what they do is they look at how much power they think there's going to be, look at how much it costs to generate the thing, solve the optimal power flow problem, and then tell the generators to generate that much energy. If you tell it to a wind farm, you're not going to get very far, right? Because the wind farm is not going to be able to ramp up power if you want it. It's just going to have whatever power actually there really is in the wind. And same with solar panels. So the technical term for this is that they're not dispatchable. You can't decide how much power they should generate when. And you can't guarantee them or really schedule them in advance. So you can certainly try to predict what they're going to do, and that's a big thing what we're doing, right? Forecasting is a big effort in how you integrate renewables. But there's still a level to which they're just fundamentally kind of different, right? We can't decide how much they're going to generate. And so if we need to know that we can produce enough power to satisfy demand, this seems problematic, right? Because all of a sudden we have all this generation that could disappear, theoretically. So what do we do about that? I should say this is essentially almost exactly one of the problems you're looking at in the extra credit problem on homework 4. If you do look at that, this is essentially a research level consideration. Maybe not quite research level, but it's sort of setting the bar for like the first thing you would do in a paper, and then you would propose some alternative approach that's a little better, and that would be a perfectly good research paper. So you do see some of this considerations already in the homework that you're working on. And just to kind of drive this point home, the big issue then is that if we have a certain percentage, a large percentage of our energy generated by renewable sources, we need still, I mean, in this country we still have sort of this notion that power should be guaranteed. We don't want to lose power. That isn't true everywhere in the world, but we probably don't want to give that up if we're going to renewables. They probably won't take very well. And so how do we guarantee that there is still definitely going to be power if we don't know that these things are going to be generating power for sure? And unfortunately, kind of the brute force solution to this is, well, we need to just increase the number of generators we have kind of standing by, ready to take over if those renewable sources fail. And this comes in two types. It comes in services called regulation services, and then services called reserve services. Regulation, so these are sort of two terms that are used differently in different contexts, but they typically mean something like this. Regulation talks about the very, very short time scale. So regulation talks about, at the level of maintaining frequency in the grid, for example, making sure that all the generators are spinning at the right frequency. When you have sudden spikes or drops in power generation, as we saw from sort of the dynamical systems, you will have corresponding, slowing down or speeding up of the frequency in the grid. And this can be a big problem because those big generators take some time to get going again, right? So if you want to spin these things up, it takes a little bit of time. And so regulation services, kind of as a broad umbrella term, refers to extra power that the grid has available whose main purpose, kind of speaking a little bit informally here, but sort of in some sense their main purpose is to maintain the stability of the grid, so to maintain frequency and to ensure that there isn't sort of a huge voltage spike or a voltage drop or a frequency spike or frequency drop due to a big drop or increase in demand. And so this, in some sense, is what can be impacted the most by renewables, because one effect of renewables is that if you have a great big solar farm producing megawatts of energy and a cloud comes over, it will instantly drop the amount of power being generated, right? And I think some people are actually working on a solar energy forecasting problem for the cloud project, and what you see is that you sort of see these smooth lines, and all of a sudden, well, there's a cloud right there, and it just drops off entirely, and you have no energy then. There's nothing like that in typical grid operation, short of a generator actually failing, right? There's something like that in sort of these big spinning machines that are very reliable. And so and the same thing happens with wind, by the way. The wind stops blowing. There's a little bit more momentum maybe in a wind turbine, but not a whole lot. Once the wind stops blowing, those things just stop. And that's a big drop in power. And similarly, if the wind starts blowing a little bit more, there's going to be a huge spike in wind power. And actually, this is due to the fact that wind, this is kind of getting on a tangent here, but the power for wind, so wind power does not increase linearly with wind speed. So this is going to be a graph of wind speed versus wind power. And it actually looks like this, the curve. It's kind of interesting. So at first, there's no power from wind turbines. Then once you start generating power, you actually start increasing with the cube of the wind speed. So power in wind, if you just look at the physical equations, is actually proportional to the cube of the speed of the wind. So there's some range here where you just really, a 1 mile per hour increase in wind speed gives you a whole lot more power. And then what happens is that you tail off. You can't keep this going on forever because the turbines reach their capacity, and so you tail off here. And then eventually, actually, they even shut down. So you get like a strong spike down, because at this speed, they actually would be damaged, the turbines, if you keep running them. And so you don't want to do that, so you just stop them. So this is, and this creates the same kind of effect as you have with solar, right? So if the wind's blowing, all of a sudden it increases a little bit. I mean, due to weather, this can happen, right? An extra mile per hour even though it's a lot more power, it isn't that uncommon to see in actual wind speeds. And so all of a sudden, going from here to here drastically increases the amount of power you're generating. And in doing so, will induce potentially, and the other way is the same, by the way, or a huge decrease in power if you're going the other way. And in doing so, can induce all sorts of pretty tough effects on the grid. So what this graph shows is the amount of regulation services measured in megawatts that you would need for different amounts of penetration of wind. So 20% penetration means that actually, I'm not sure if this refers to total penetration or if this refers to new capacity, but I think it refers to total. It doesn't really matter. You can look from the study. This is a study done by the ISO of New England. That's the system operator of New England. And they essentially looked at how much of our power generated by wind, given different amounts of power generated by wind, how much more regulation will we need than what we have right now. So right now there's a fairly small amount of regulation because most power can be kind of controlled pretty reliably, right? We sort of know what's going on. These two things, so partial queue and full queue, those are actually projects that are currently scheduled. So these are wind farms that are currently either in some stage of the planning process. And if we just finish all of those things, then we'll need a doubling in our reserve capacity. So we have to go from 82 megawatts to 161 megawatts, just by completing what we already have. And as you see, even going to like 20% of our energy from wind, we can need a huge amount of increase in regulation services. Because, as I said, wind is of this type that the power can spike and drop very quickly. So we really need to be able to react very, very fast to effects like this. These two columns here, by the way, the difference is this is 20% balance. What balance means is, in this context, I think, if I recall the study correctly, is that there's some offshore wind and some onshore wind. So if you've heard of offshore wind is just you put turbines out in the ocean. The advantage there is that offshore wind is a lot more steady and predictable than onshore wind. And so if everything is the best of all possible just onshore things, you actually need more regulation than you would if you mix offshore and onshore wind together. That's why those two columns are different. But I think what it really highlights here is just how much more, I mean, this is a huge increase, right? And we're talking about only 20% penetration of wind. How much more generation capacity and more stuff you need to build in addition to just wind turbines if you do want to use them, right? So it's great to talk about building wind turbines. I think it is the thing we should, this and batteries and all this kind of stuff are things we should be talking about. Actually, by the way, I should mention that if you have reliable storage, this hugely cuts down on this effect, right? Because all of a sudden now you can go from not knowing anything about when the wind is going to blow or not to when it's blowing too much, you store it in a battery, and otherwise that actually levels it out. But at least given the current kind of technology where batteries still aren't feasible, though I know people here are working on that, aren't economically feasible yet at least, it requires this huge amount of new power plants to be built that aren't wind turbines, right? So you need you have all these wind turbines, you just need to build more other stuff. And they're usually gas-powered plants because those are the ones that can spin up really quickly. So this sort of speaks to the needs there. We also need additional operating reserve. And reserve is like regulation, but it's a little bit longer time scale. So now we're talking about like a 5-minute time scale or something like that. Regulation has to spin up immediately because you basically have to use it to stop the grid frequency from falling apart. I mean, that's really important, right? Load cuts out right now, or load increases right now, you need to immediately step up some generator to stop the frequency from just oscillating wildly, or even not oscillating, just falling wildly. Reserve is more something like, well, we know that the total power consumed, so ignoring frequency, just thinking about total power mismatch between what's being used and what's being generated, we know we're not going to be quite right in our forecast. So we're going to have, on the level of 5 minutes or so, we're going to have some error. And so this we also want to be able to account for. But this actually happens right now still also, right? So certainly even if you schedule big generators, which you can schedule, you're not going to be exactly right in your predictions. And so you're going to have a little bit more what's called spinning reserve, though not all reserve is spinning reserve. Spinning reserve is the type that's called spinning reserve because it's a generator that actually is moving. It is spinning. It just hasn't been hooked up to the grid yet. And so the same story happens for wind. It's a little bit less drastic in terms of the percentage increase because regulation or reserve is something we already have going right now. But this still speaks to just how much power we have that's kind of always operating but not actually being used. So what reserve is this power is kind of ready to go that isn't actually hooked up to the grid yet. That can kind of be dispatched within about 5 minutes is a sort of a typical amount of time it'll take to dispatch some new power. So I guess you think of regulation as like on the order of 10 to 30 seconds or so kind of response time, and reserve is about 5 minutes. This varies. This is not. That is variable, the actual amount of time you have. So like some regulation signals come out every couple seconds, but we're talking about that sort of time scale here, and then like the minute time scale for reserve. And so here, it's not quite as drastic, but you still do need a lot more of this when you have wind. And that, again, comes from the fact that wind is less reliable than other things. Well, reliable is wrong. It's just not dispatchable, right? So you don't know that it's going to be coming. And so you maybe need reserve to kind of account for like those sudden changes. But then even after the sudden change, you still need something that'll ultimately make up that big power difference that might happen if all your solar panels go out or they have a cloud or something like that. So that kind of makes sense. I mean, this basically keeps up with those sudden drops. It sort of focuses on those things immediately, and then you have some time for the reserve to kind of catch up to a new average. And well, the regulation kind of just will track very, very sudden changes. That's the basic process. And again, the point is that doing this, and then 20% is not that much wind penetration, really, right? It's not like a huge amount. And the forecasted load for New England was about, in a lot of these studies, I guess it's today's. I guess it isn't today anymore. I think when I made these slides, which was last year. So last year at this day, about the forecasted load was about 17.5 gigawatts. And so this many megawatts, this is a sizable fraction of the total amount. We're not talking about a small amount here. We're talking about a lot of operating reserves that are actually just sort of spinning there. A lot of them are spinning there, not doing anything, just because we don't want to lose power at any point. We don't want to have blackouts. So big picture again. The challenge here is that we do want to deliver power reliably. When you start integrating large amounts of renewables, this becomes a lot harder because now all of a sudden you cannot tell the renewables what to do, and you have to account for their sudden spikes and decreases in power. This in turn requires that we build a lot more new capacity that is not renewable, and this becomes a big problem. And so how we deal with that is an ongoing research problem. I should add that a big way to deal with this, by the way, is better forecasting, right? If we can forecast things better, then we can tell the sort of traditional generators, say the reserve generators, to not always be spinning, to be sort of shut down for real for a while, and maybe only spin up when the wind's about to drop, because we know it's about to drop because we have some forecasts about this. So if we are able to do better forecasting, this can be hugely beneficial for decreasing the amount of operating reserves we need. And this is where kind of these ideas of prediction and forecasting come together with topics like renewable integration. And that's why these things are kind of inextricably linked to a certain degree. OK, any questions about this? Again, I'm just presenting the problem here. I'm not presenting what you do, though, of course, we are doing some stuff like you see on the homework. You're doing some of it already, so you have some idea of what you do with better predictions and stuff like that. Any questions? Oh, I have more slides on this. Shoot. So first of all, right. That study here. How did they come up with it? How did they get these numbers, right? Well, it actually is exactly what the homework assignment talks about. What they do is they just run simulations. They look at what's happened in the past. They create a simulation of the grid itself. And they see what happens to optimal power flow when you have these uncertain sources which they can't predict. Well, how much more do you actually need to be able to dispatch? And that's exactly how they come up with these numbers. It is nothing more sophisticated, though that already is pretty sophisticated, right? Building these big simulations, doing optimal control. This is how they come up with those numbers about how much more reserves and regulation you need. I should mention another line of work, which I think is really cool here, because from an academic, so from a sort of a practical standpoint, a lot of these studies are very good because they use a lot of real data, these real grid simulation, all this kind of stuff, but they don't give that much intuition kind of about the fundamental mathematical structure of the problem, right? They're just sort of, here's the results you get when you run a bunch of simulations. There's also a lot of really cool work on a little bit more mathematical formulation and how you do these things optimally when you have certain, essentially certain special cases of this renewable power generation. How can you solve dispatch optimally? Remember, our operating paradigm for how we did this kind of stuff under uncertainty, how we do optimal control under uncertainty, was this model predictive control method, right? So we do our best job of forecasting right now. We do take actions based on that, but then if something else happens, we adjust to that. That is not optimal, as I said. That is a suboptimal strategy, which just happens to work well in a lot of cases. What's really neat is that people actually can, for certain special cases, they can solve these things actually. They solve the full stochastic optimal control task, again, under certain simplifying assumptions. And they can show what the absolute best thing to do is under those circumstances. And that can actually, in and of itself, mean that we require less reserve, right? Just by doing a better job of allocating power given our current understanding of the uncertainty in our forecasts and the uncertainty in the grid itself. And these are two papers in that mold here, which again, if you download the slides, you can click and get a link to and you can read them. All right, so the next topic I want to, and I guess I'll mention this, are there any questions now that I've actually finished this little discussion here? Okay, so let me talk now about grid security and resilience. So in power systems, security typically means two things. One of two things. I guess both at the same time, also sometimes. As the grid becomes more computerized and we have more automated control, the typical kind of computer security, just cybersecurity, becomes more and more of an issue, right? Because all of a sudden now you have potential for attacks on generators, stuff like this. There are various videos, I think, of people gaining access. I mean, as a demonstration, not in reality, but as a demonstration, people can hack into generator systems in the actual generator and essentially break generators by entering bad commands into a generator system that they've remotely controlled. So this possibility exists, and it's kind of frightening too. Is if everything's online, we know how safe computer networks are. They get crippled occasionally. We don't want that to happen to a grid. And so a big issue is just the typical kind of cybersecurity. How do we secure these computer systems? How do we make them resilient to attack? Or how do we detect even if it's being attacked, right? And these are kind of typical, for the most part, typical kind of computer security related lines of work. So there's a lot of work in cybersecurity. How do you secure computers? And for the most part, though there are some ways in which there are some challenges that are specific to the grid itself. A lot of these general threads of research are very similar to the corresponding ones for just cybersecurity, right? And it's certainly a very important area here because we need to secure these systems that they're going to be more automated and more controlled. The second meaning of security, though, is really this is more the power systems meaning. This is more about system security or resilience. And security here means that if something unexpected happens, like a generator goes down or a transmission line goes down, will the whole system collapse? I guess it can be from malicious actions too, but it's much more from a power systems perspective. Is this system stable or unstable under the conditions of something failing? That's sort of the basic principle here. And so I'm calling that here grid resilience, I guess. I'm mainly going to be talking about this, not about grid security. But here, And I should say there's a bunch of papers linked on both these two topics here. But here the problem is much more of one that we already have the tools to deal with from this course, right? Because we've built the simulation models, and what we can do is we can test them under different component under the assumption that different components fail. So we test our power flow solver. All of a sudden we knock out one generator and see if we can still solve power flow or optimal power flow. This is something often called security constrained optimal power flow. So you might see the SCOPF, security constrained optimal power flow. And what this asks is, typically, if one line or one component fails, usually one generator, but sometimes one line too, can we still get a solution to our optimal power flow problem? So typically optimal power flow, right, you just solve it once. The system is as what it is, and you see what the optimal allocation is of different generators. This asks, if we knock one of them out, and we sort of knock everyone out in turn, does a solution still exist? Or if we knock one transmission line out, does the solution still exist? And so this is more the security side of the power, the more the power system side of security deals with things like this. And I'll give one more example of what can happen there. So let's talk about, we're talking about resilience here. This isn't quite the optimal power flow problem. This is really much more the control at the fast dynamics level. And this deals with things like blackouts. So it's a toy problem. It's not a realistic size scenario, but it's not completely dissimilar from what can happen in reality. So a big problem in the grid is resilience in the face of generators failing, right? And one way we can see this, we can see what happens here very clearly, is that let's take our favorite dynamical system now that you're all very familiar with and very experienced with. This just equations of motion for these generators and a DC power flow approximation. And let's look at a simple controller that just does frequency regulation. So here we actually don't even care about tracking the absolute angle. We're just going to track the reference velocity at all the generators, which is actually more what happens in the real grid, because tracking an angle exactly in the real grid, I mean, it really doesn't matter what your absolute angle is. And to track angles, you need to know what your angle is relative to someone else's angle, which can be tricky to get. There are ways of doing that, but you need essentially GPS clocks to do that. So what's actually more common is just to do frequency regulation, just to fix the frequency to be the reference. Try to make the frequency match exactly the reference velocity of the whole grid. So this control law here is actually just an example of a simple. It's actually PI control, but it's actually more, in our context, more like DI, because we're just tracking the derivative term here, which is the angular velocity, and we have an integral term. Okay, so this is our setting. We have essentially a simple controller at each generator running our system here, just trying to track reference velocity. And that, in turn, by the way, will provide enough power for everyone, because if everyone is if all the generators stick to their desired frequency, somehow they will combine. They have to provide the required power. We don't quite know who will get it, but together they will do that. So here's what happens under sort of normal operation. So what I did here is I simulated the system using some time varying loads. That's why there's a little bit of with some noise in the system. That's why there's a little bit of jitter there. But as a whole, all these generators, they follow exactly what they're supposed to do. They all maintain frequency. So that this plot here is showing their frequency minus the reference velocity, minus the reference frequency. So they do exactly what you've seen in PI control. Or in your PID control if you have the derivative term too. They work. Everything works fine, right? This is what a lot of generators actually do. So now I'm going to throw a little wrench in the thing and everything though, and say that at time 100, I'm going to knock out generators 1 and 4. I'm just going to stop them. So they break or something. It's pretty catastrophic actually, but 2 at the same time. But let's just assume 2 at the same time break. And now something really sort of bad happens. As you can see, their effective angles, and what their angle is at, Every node has a power angle, regardless of whether it's an actual generator or not. I mean, loads all have a power angle at that load too, so we can track their angles even if they're not a real generator. What happens here is that when they go out, as you can imagine, their frequency, the other generators in the system don't really know what to do from this, and so their frequencies at the generators start oscillating. Now the other generators, that PI control is still going to try to provide power for everyone, so you still can sort of, you don't completely fly off everything here. It's not like the system breaks immediately, but this is not a good scenario here. This is these things oscillating, and they actually will keep getting bigger and bigger oscillations and eventually blow. I mean, eventually it goes, in theory it goes to infinity, but in practice everything just breaks. And one thing that actually happens is it's obvious. So the blue line here is generator 1, the cyan line is generator 4. Those are the two that go offline. But what you can actually see here is this green line here is also, that's generator 2. That one is not down, and that frequency is also oscillating. So it actually turns out that it's not just unstable. The system is not just unstable for the 2 generators that went down. It's unstable everywhere. And so what will happen if you just let this go is that all the generators will just break. They will actually, I mean, what would happen physically is that they would try to be turning too much and changing frequency too often, and their shafts would break. They don't want to do that, so what generators will actually do instead is save themselves and myopically, say what's my best thing to do right now? Well, if I keep going, I'm going to break. That's probably a bad thing. I'll just shut off instead. So all of them shut off because they're all unstable, and the grid blacks out. Now, the interesting thing here is that, and again, this is all generators independently executing that PI control loop to regulate frequency. What's very interesting here is that there's no need for this to happen. So if you look at the system as a dynamical system and think about only 3 generators being there instead of 5, this system is still perfectly controllable. You can actually guarantee that every node in the system has 0 deviation from in its reference velocity, or in its velocity from the reference velocity, or on average 0, while only using 3 generators. So formally, what we sort of know what this means is that if the system, if you write those A and B matrices, the system is controllable if you only look at 2 columns or 3 columns of the B matrix. This means that if you were to run LQR or something like this, you could actually completely control the system. Everything would be fine. So in some sense, if only the generators knew to talk to each other. But right, LQR requires that you do something more complex. It requires that you actually, that the controllers at every generator know what's happening to all the others. Right? Because they require, they sort of, remember the K matrix is a dense matrix. And so you actually need the state information not only at your own node, but everywhere else too. So what that sort of implies here is that if everyone would just communicate a little bit and say what's happening to me or to others, you could avert the situation. And I've heard sort of folklore say that every outage that's happened in the last 20 years was perfectly preventable if you knew if all generators simultaneously knew what to do at the same time. What's the problem is that they don't know what to do. They see myopically, sort of looking only at their own system, that things are going badly, and that they know if things don't change, don't get better everywhere, that they will break, and so they shut off, and that makes things worse everywhere, of course, and it kind of cascades like this. I don't know if this is true. I don't really know about historically what the outages have been like, but I have heard sort of tell that essentially every one of them has been preventable if all the other generators that were still good could have properly collaborated to try to fix the problem. So if only we did better control of these things, we would not have problems like this. This is in the US too. I think there are other countries where there's just too much demand at a time, so you could not actually provide enough with power generation. But at least in the US, we have tons of capacity here. We could always provide the power that people need if only we knew how to control the things correctly. But at the same time, this is not an easy problem, right? Because they have to communicate kind of instantly know kind of the best strategy to employ all the different generators. It's not easy to do. And this is a big line of research, is sort of how can we get to sort of get close to this kind of theoretical optimum where we know that if everyone sort of knew exactly what to do, everything would be great. when we are constrained with things like, well, you can't communicate instantly with everyone else, there's some delay in communication. There's probably some, if these things happen at a fast enough time scale, that maybe that communication is going to be too slow, so you're going to still fail anyway. So you probably don't want to, put too much faith in what's going on, or too much faith in sort of the large-scale global control procedures. So how do you do this kind of in a slightly more narrow, myopic way that still can guarantee stability for the grid as a whole? Sort of a very ongoing and very cool line of work. All right, any questions on this one here? All right, so let's talk about demand response now. Who's here that has heard the term demand response, actually? Okay, pretty much everyone. So demand response refers to the fact that in this course, we, for the most part, treated load as being fixed, right? We said that there's this PL, it is what's given by the problem, and you have to schedule generation to match that. And this typically has been the operating mode for the grid. Maybe, in the horizon of years, we can start to do things like efficiency and make people consume less power by whatever thing we want to do to deploy more efficient appliances or whatever. But at the level of right now, we treat demand as being inelastic. It is just whatever the demand is right now, that's what it is, and we have to provide whatever power we need to keep up with that. This is starting to change, though. And as you have things like more renewables and all of a sudden more variable sources of power, the fundamental principle here is that all loads, in some sense, have to be on exactly when they are on, right? That's sort of what the underlying assumption of this fixed load or fixed demand, inelastic demand, I should say, is that there's no differentiation between types of loads that we have, right? We have to just satisfy them all. But in reality, there are plenty of loads that don't actually need to be run all the time. For example, an air conditioner doesn't need to be run necessarily right now, as long, right? Air conditioners usually work, as we saw before, heaters or air conditioner work by, kind of going on and off on some schedule to maintain temperature within a certain range. Well, if it turns out that this very second, we've just lost a lot of wind power, I can probably go ahead and turn off my heater right now, not even to, cool down the room any more outside of its range, just to essentially cut power right now, right? So here's, if you look at sort of like a temperature in a room, and we'll say we have this is a heater, so we'll say we want to run a heater to maintain temperature within some range here. So if it gets here, you turn it on, then it settles back down, right? So like this. And so what this looks like for the heater is it's on here, then off, then on again, then off. Now, if right here there is a power, some big loss in power from a wind farm, well, it's fine for us to turn it off. We're here in our temperature. It's fine for us to let it just sort of settle down here. As long as we know that we can turn it on eventually, maybe at some point during this new fall time, we turn it on here instead. This is a perfectly good, I guess this is let's see, how would this actually look like? Look like this, right? Something like that. This is a perfectly good schedule too for the heater. There's zero difference, really zero difference from the standpoint of even our kind of arbitrarily defined objective here, which is to keep it within that range. We're not even talking about making people more uncomfortable, right? We're just talking about literally things that they, by definition, will not notice because we've prescribed it as just keep it within this range. So if we were more intelligent about this, then we can sort of realize that not all loads are the same. On the other hand, I probably don't want to turn off the lights, for example, in a room at night if there's no power, right? So there's all this differentiation in the type of load that we have. And also, I should say, this goes beyond just kind of rescheduling things. But it can be things like, well, maybe if it's a hot day, I'm willing to have a little bit higher temperature in my office. I don't need to cool it down to whatever crazy things all office buildings in the US cool temperatures to during the summer. I'm OK doing it 74 instead of like 72 or something. So something crazy like that, right? So there's both sort of things you can't even notice and the things that you do notice but that are very minor effects and aren't going to really affect anyone, versus things like, if my computer turned off while I'm at the office one day, I probably wouldn't really like that. I'd rather they turn on the air conditioning a little bit, or turn up the air conditioning a little bit, down or up. Make it less cool in the room. And this kind of encompasses the basic idea of demand response. The idea is that there really is some elasticity in demand, fundamentally. We just need to put in place the infrastructure that can realize that elasticity, so that we have the ability to, say, control an air conditioner and turn that down when the grid needs it, but don't mess with my computer, because that I don't want to leave. Maybe if it's a laptop, actually, it will be OK. But if it's a desktop computer, I don't really want it to be shut off just randomly when I'm working. And so demand response, and this has been known about for a while, but I think it's becoming more. It becomes more and more, tying everything together, it becomes more and more important when you have high penetration of renewables, because these are the things that kind of necessitate a lot of these changes. There is becoming more and more emphasis on the ability of power operators to control loads to a certain degree. So rather than just having our optimization problem over PG, right, our generation, we also include a cost on load, right? So in optimal power flow, what we had before was something like minimize over the generator power, sum over all I from 1 to n of the cost of this generation, right? Subject to power flow constraints and everything else, and generator constraints, and et cetera, subject to whatever. What's happening here is that now we also have the ability to say, OK, there's a cost to load, but there's also, there's cost to generation, but there's also a certain extent to which we have control over load too. So we also are minimizing sum from I equals 1 to n of the cost of the load. Now the sign convention here actually is whatever you want. You often see it negated like this, because you think of more load as being, or rather decreasing a load as being less costly. So you can have the sum, but that's a sort of a sign convention here. I'll put like p tilde or something like that. So there's a different cost in that one. But basically, from an operator standpoint, decreasing load is just as good as generating more power. It's the exact same thing. So if we have some cost curve that tells us how much cost do I incur by decreasing my load a certain amount, basically, and that'll look the opposite from if you plot the load here, so this is PL. For generation, it always costs more to generate more power here. I guess thinking about this being kind of the value that's negated here. Now for load, more load costs us less, right? So it kind of looks more like this, right? These cost functions here, because more load is sort of what people do anyway, and so it actually costs us some money. This shouldn't ever go negative here, or shouldn't ever sort of reverse direction. More load rather will cost us some amount of, less load costs us some money to get, right? We have to sort of pay some cost, paying the people to turn off their air conditioners or whatever. We pay some cost for having less load. So the costs are kind of reversed like this. But under that formulation, you can actually now optimize. And of course, we also have constraints on this too, right? We have constraints that we can't shut off load entirely. We have bounds on load just like we have bounds on generation. So if we have this scenario, we can now optimize our same optimal power flow problem subject to the fact that load itself is a variable in our problem, and we can control it to a certain degree. And this will change everything. I mean, not everything, but it changes the things you expect about optimal power flow. You now have different prices at different nodes, because in computing the prices, you take into account the prices that you can gain or lose by increasing or decreasing load. And you just have much more flexibility in your problem, because if you do have a case where, say, again, using the example of renewables, where you've just lost a ton of power, you can't get going fast enough again, you can accomplish that same thing by cutting the load a little bit, temporarily maybe, and then ramping it back up once your reserves can come by. So this ability, depending on the speed of it, can act very much like regulation or reserves. It can kind of actually take the place of regulation or reserves, because from a grid perspective, there's no difference. It doesn't matter if we're generating more power or using less. That's the same thing. So I want to give and this is not a new idea. I mean, even at this point, this was well known, but this is a well-known paper on what happens to the economics of essentially optimal power flow when you factor in the fact that demand has some elasticity to it. So I want to give one example of this. And this example, I'm citing a bunch of different papers that essentially we're continuing this line of work here. But essentially, this example is actually more to the first thing I talked about, which is just these thermal loads you have, like heaters or like air conditioners, where we don't even want to change the actual operation of them. We want to keep temperature within a bandwidth in the same way as we were before. It's just that we want to do so in a way where we can reschedule when they turn on so as to effectively provide some very short amount of demand response to the grid. Does that make sense? So what we're doing again is switching from a heater or an air conditioner going like this very regularly to going like this, right? So wait for a while, now it's good, now it's bad. And basically doing this intelligently in a way that matches, tries to decrease power slowly or quickly. Now, if we only have one building, I should add, we are somewhat limited in what we can do here, right? Because with one room, if you happen to be, if you're not willing to tolerate any change in your actual operating conditions of your room, and it turns out that, so you're going along and you have your temperature comes up, goes down, comes back up. And say, for example, that there's a huge, decrease in wind power right then. So right at when your power's the lowest. Well, unfortunately, you can't really do anything about it in this one house, right? Because you haven't used, you're sort of at the lower range anyway. You have to turn on the heater at this point in order to ensure that you meet your comfort conditions. So with one building, you're somewhat limited in terms of what you can do. The idea behind this work is that if you have lots of different loads, all different types, doesn't matter what they are, but if you have lots of these things, the chances of them all being at this point here at the same time is very low. So chances are, if something bad happens, some of your loads will be up here, or maybe in the charging stage where they would normally keep charging, but they could just turn off instead. I should also say this is effectively that this whole idea effectively is just storage, right? Storage of energy. It's just storage of energy as sort of thermal mass, I guess, right? We're storing energy effectively in things we're doing anyway, which is heating up a room or cooling it down. I think these both talk about air conditioners. They're actually talking about cooling things down, but the diagram's the same, just in the reverse order. This is in the opposite direction, everything here. So the problem with this, though, is that if you think about the communication needed to really do this in the most obvious way, the operator would need to know where everyone is in their charging cycle and then be able to tell everyone what to do. That maybe isn't the most realistic scenario, right? Because I don't know if you're going to be able to get every refrigerator in the state to send you a signal. Maybe you won't even get one to be able to turn on and off, but that, just getting a refrigerator to putting a little chip on a plug seems a lot easier than having everyone have to remain on the internet and tell you exactly what's going on right now. So even the idea of just listening to a signal seems a lot easier than communicating back to the central server, telling them where you're at here. So typical MPC, for example, would require that we actually know where everyone was. And so what this one line of work looks at is instead, let's look at a little different scenario, and let's look at control laws that only require a single action to be broadcast to everyone. Right? We don't want to get to a situation where we have to send a million different signals out to a million different refrigerators. That seems like it would be a lot of work on the side of the whoever central operator is. And we also don't necessarily want them to have to each individually tell us what's going on with their power. So instead, we want to be able to sort of send one signal out to everyone and then measure an aggregate signal of the entire grid and somehow make that still work. And so what these two papers do is these two papers sort of go towards that direction. So the idea is instead of having our state be essentially the position of, and I don't worry too much with this figure, it's somewhat confusing here actually. I'll try to describe what it is informally. But basically the idea is instead of having the actual temperature of the system be our state, and that would be the temperature then of every single device in our system. So that's hundreds of thousands of different refrigerators. What we do is we first of all discretize the state. So that's the first thing, is because it's easier to deal in this scenario with discrete quantities rather than continuous quantities. So we take our temperature range and we chop it up into bins. So temperature, chop it up into bins. And then normally for a single device, the state, the effective state would be, well, it would be a 1 whichever one you're in and a 0 everywhere else, right? That would be your state to your system. What you can do instead is have the state be an actual probability vector that represents where everyone is. So instead of the state being this, what you do is you look at every single appliance and you basically say, well, how many are in this position here, at the lower range of their temperature. So maybe there's, 10% are there, 2% are there, 2% are there, 5% are there, and 0 everywhere else. This is uncommon. This wouldn't really happen, but just say it's like that. Usually you have some in every state. So this is our new state. So now we've represented the state of all these hundreds of thousands of systems potentially by just a single vector that's relatively small dimensional. And this diagram here would, and the end bin there is a number of chops you make for your state, or maybe the number of chops divided by 2 or something. And this figure here shows the dynamics of the system. So actually, I should say one more thing. There's actually 2 states for each thing. There's a state that describes the temperature for each guy, and there's also a state that describes whether it's on or off, right? Because these things, they also either are consuming power or not, and that actually is an element of the state as well. It is affected by control, but we're going to call that an element of the state for each of them. So you have some proportion that are these temperatures that are some portion are on, some portion are off. And what that is this diagram here. You have these discrete states here, and on the top you're on, and the bottom you're off. Okay, so now what? And the arrows here show the dynamics of the system. So essentially, if you are off, this is a refrigeration task or air conditioning task. So if you are off, your temperature will start to increase with some probability. Those probabilities come from the fact that these are now, we've discretized the system, so you have, it's like an MDP effectively, and so you have some, you might stay in this certain state, or you might go to the next one with some probability, essentially. And so the arrows show, essentially where you are, where the things are in this off state and on state cross product with where you are in temperature. Does this figure make sense here at least? And also now at any given state, if you want, you can make some number of the appliances switch from being off to on. You can make them switch to on to off too, but basically you can not only move this way due to the dynamics of the system, you can also switch whether you're in the bottom row or the top row. So what they do is, actually maybe I shouldn't. Okay, so let me say one more thing, because I think it's not quite described on this next slide. What they do is, remember, one of our goals was to have a single sort of control action we could send to everyone. Right? We don't want to get into a habit of having to say, okay, well, you 10,000 refrigerators you turn on right now, you other 10,000 you turn off right now. What they do instead is they actually send a control signal that is a sort of a random quantity. So they send a control signal that says, essentially, for each bin, they give you a probability of turning on for that bin. So they send the signal to everyone that says, if you are in this bin, then you turn on with probability 0.1, and then each refrigerator itself just sort of turns on or off with probability turns on with probability 0.1. If you're in this bin, you turn off with probability 0.1 or whatever. Does that make sense? So basically, you send one signal out to everyone, that encompasses what everyone should do with what probability, and then each one executes it all independently. So that you don't need to actually maintain different states for different devices, or even send different signals, different control actions to different devices. You just send one big broadcast action, and what comes back is just the sort of new state that you get from every one, which you can measure just by doing aggregate measurements without measuring every one in particular. Okay, and just now, I won't get into details too much here, but essentially what they show is that this formulation actually you can write it as our favorite dynamical system there. So this is exactly what they're doing, actually. They're writing it down as a partially observable linear dynamical system. You can formulate this in that setting. And now they just do, I mean, this is exactly what we know. This is exactly MPC objective for this dynamical system. They have some dynamics up there. They have some constraints on the control. These things constrain the things, for example, it's like to be a probability vector, and you never can tell people to turn on more than 100% or less than or off more than 100%. And then, given that, you minimize some quadratic costs. This is exactly the form that we see. You basically have some penalty on how much you want your total power to deviate from some set point you specify, plus some cost on the control on telling people to sort of switch. You don't want them to sort of switch too much. You penalize them from switching too much. Plus some deviation from the actual set points themselves. You want them to stay as close to the middle of the range, for example, as possible. So this control objective is exactly model predictive control, and it's applied to this dynamical system of air conditioners or refrigerators communicating to sort of figure out what all to do. And it works really well. What they're able to do is using, I think, 200 here, 1,000 different air conditioners, or TCL stands for thermostatically controlled loads. That can be refrigerators or heaters or electric heaters or air conditioners. What they show is that if they have desired trajectories to follow, so this is sort of the red here, which you can't even really see because this follows so well, is some desired trajectory that they want to follow for these sum of all total refrigerators. And what they show is that using this simple kind of control law, they actually can track this very accurately, even though what everyone actually is doing up there is very different, right? So that graph on top shows you where each of those air conditioners are. And that varies a lot because they're sort of all doing crazy stuff. One may not be able to turn off at any given time. But in aggregate, they're able to track these kind of very either steady or oscillating or kind of random patterns of desired power output from all of them. Now, this has to be zero mean, I should say. Sort of the ultimate signal has to be zero mean. Otherwise, you're asking them to actually use less power in total, which we can't do while keeping them in the same band, right? But as long as the signal you want to track on average is zero, then sometimes we can be above, sometimes we can be less, by essentially telling them all to charge when we want it to be less, or want it to be more, and all to not charge when we want it to be less. That's the basic idea here. And you see when the power kind of dips down, you ask it to do a lot less power, all those things rise up to a high temperature. When you ask it to do use a lot less power, they all sort of go to a low temperature. When you ask them to do a lot more power, they go to a low temperature, right? So here, this makes it low. This here makes it all high temperature. So it's sort of very intuitive, but you can track these sort of pretty complex patterns using methods like this. The last thing I'll say, and I actually have the least slides on this, so I think I can finish up in the time we have left, is a topic called microgrids. And microgrids are also a very hot topic of research right now. And what these are is essentially, conceptually they're very simple. It's just if we take a small electrical grid system, so say in the order of a college campus, or it's a common example actually for microgrids, or even a neighborhood, something like that. Typically right now they get all their power from the grid, right? So they're sort of tied to the grid. They can't really do much if their main line from the grid cuts off. What a microgrid does is it actually builds a lot of the capabilities of a full grid system on the scale of a much smaller, at the level of the much smaller system. So you'll include in your college, say, you'll include a generator there and storage if you want storage. You'll have some renewable generation maybe. All these things together to essentially provide all the capabilities of a full-scale grid in a smaller scale. Is all it is. I mean, microgrid just means a small grid, really small grid, I guess, a micro. And there's lots of papers on this, and even more if you just Google microgrid. There'll be tons of things will come up. Now, the benefit here is that they can, at least in theory, provide more efficiency or reliability than the grid, right? Because in theory, if you can provide everything locally and power goes out due to some crazy planning problem far, far away, you can still provide for yourself, maybe over a short period of time, given what you have right now. So typically, this is sort of drawn with figures like this, where you have these some sort of grid connection that connects everyone to the grid. But then you also have these little circuit breakers that behind the circuit breakers have both generation and loads. I guess these little these things here are generation and load. I mean, the arrow is usually a load, but the up arrow and down arrow are generators and loads. And so the idea here is that you, in addition to having just loads and at the consumption side, you also have some generators throughout, and you also put in some circuit breakers throughout this thing, which basically can disconnect your system from the rest of the grid. So as long as you have a generator behind your circuit breaker, you are potentially OK, right? So what you see here is like this system is just loads, so it doesn't have a little square, which is a circuit breaker. Everyone else that has a square has a generator behind that square. So you have the ability to generate power behind the circuit breaker point, because if you cut power, you need to be able to actually provide it somehow. And conceptually, I mean, I'm not really going to get into any detail here, just to say that this, how you do all the things we talked about before, how do you do scheduling, how do you do optimization, how do you make sure that energy is used as efficiently as possible, all these things become interesting questions at this micro level too, because now you have sort of very small amounts of generation maybe, you have some storage, you have all these different, you have a solar panel maybe, and you want to know what's the best way to control all this together at a very small scale. And furthermore, how is that going to interact with the grid as a whole? If I start doing things like cutting off my power or generating my own solar energy, stuff like this, how does that actually work with the rest of the grid? And so these things are again being researched very heavily right now, and sort of how do you do the same stuff we're doing currently at the large scale at this small scale of small neighborhood or campus size grids. I think that is all that I have for these slides here. So are there any questions about that? I guess I didn't ask for that for this one, about either of these two topics. Any questions? All right, well, in that case, I will see you next Tuesday.